Hello and welcome to the next part of our series on using OpenHFDIB-DEM together with OpenFOAM. Today we will be talking about discrete element method settings in our solver. So let's go for it, and that's today's topic. And first, let me just remind you where we are on the general course outline. So first, we kind of gave some overall general information about our HFDIB-DEM library. Then we went through how to add solid bodies into computational domains and covered the fundamental movement modes of those solid bodies in the domain. And today's topic is the discrete element method. So mutual interaction of solids in computational domain. So now let's go for it. And with respect to the workflow, as usually, we will be modifying, well, almost exclusively the HFDIB-DEM dict in the constant directory. And in that dictionary, we will focus on DEM subdictionary, which contains the DEM settings. So for example, the time step for discrete element method, definition of solid materials, definition of collision patches for solids, and general contact treatment. If you are interested in the code, today we will be still using our pure DEM branch of solvers, so our HFDIB-DEM pure DEM solver, and we will be working with discrete element method engine, which is in the source directory and it's driven by the OpenHFDIB-DEM main file, and concerns also the contact models, geomodels, and virtual mesh code parts of the code. To be able to follow this tutorial, you need to have OpenFOAM 24.12 installed on your machine, and you should use the version of the library provided to you either as the course at Guimarães or available through the link below the video. So now let's go for relevant capabilities of our library, so relevant for this particular video, and it's the discrete element method. So our probably most important setting is the discrete element method integration step, which is roughly independent of the integration step used for CFD. So in our setting dictionary, we have this step-DEM entry, which is a factor of the CFD time that should be used for discrete element method. To give you a way to set up this step-DEM, let us take a look at some estimate for overall collision time of two elastic spheres. So this is based on Hertzian approximation, where we have some material properties such as reduced or effective Young modulus of the two particles. So we have Young modulus of one particle, Poisson ratio of one particle, and the same for the other particle. Density of this particle and characteristic length of these particles. We can use these to estimate the total collision time, and then we use the soft discrete element method approach, so we allow for small overlaps, and we need to integrate the contact forces over this whole time. So there is general rule of thumb that the delta T for DEM should be roughly this total collision time divided by 100. And this gives us estimate for step DEM entry in the dictionary, like this. So that's one thing. The other thing is definition of system boundaries. So at the moment we can work with planar boundaries, where each contact boundary needs to be defined through point lying in that contact plane and outer normal vector to that plane. And finally, if we have integration step for integration, we have the solid bodies that can contact. We have collision patches or collision boundaries with which the solid bodies can come into contact. We can take a look at computation of the actual normal contact forces. So this, once more, we work with a soft discrete element method. We allow for small overlaps, and we use this small overlap to scale the magnitude of contact force, and in our case the size of the overlap is expressed through overlap volume. So is the volume shared between the two bodies in contact. The direction of the contact force is expressed through contact normal, and of course the contact force itself depends on material properties. So we have this effective Young modulus, which itself depends on Young moduli and Poisson ratios of individual materials. Then we have a coefficient of restitution, which is responsible for dissipation of contact energy. And because we work with different shapes of solid bodies, we have a curvature coefficient in here, which is hyperparameter of the method basically. How it looks in our DEM subdict of HFDIB-DEM dict is this. So we have our curvature coefficient, which due to consistency with standard Hertz model is 0.55 for spheres, and due to consistency with the Chen 2012 model for planar contact is 4 for planes. Then we have rotation model. Our default choice is Mindlin 1953, but there is also Chen 2012 model available. And we can define materials. So as said before, each material has its own name. So we have this particle material, then it has Young modulus, Poisson ratio, friction coefficient, and coefficient of restitution. And in here we have standard ranges for all of these. There is one more entry, adhesion normal coefficient, but this is kind of experimental feature at the moment, so I will not go into detail on that. Then we have these collision patches. So as before, let's just go back. We have this bottom collision plane, and we define it through point lying in the plane and normal vector. We have this bottom, which is unique identifier of the collision patch. It has material, in this case this one material, and there is a normal vector and point in the plane. This completes the definition of collision patch. Now we need to take a look at geometric properties of our contact. So overlap volume, which is used to scale the magnitude of contact force, and contact normal, which is used to get the direction of the contact force. For spheres, it's pretty nice, because for spheres in contact you can compute the overlap volume analytically, and you can easily get the contact plane, thus the contact normal. For STL based solids, it's slightly more complex because we do not have any analytical expression to work with. So we came up with this virtual mesh approach, which is purely discrete, does not touch the CFD mesh due to the performance reasons, but instead in the vicinity of a contact we construct this bound box that will contain the whole contact, and we adaptively refine the bound box to some subvolumes when the subvolume is cut with at least one of the bodies. Then we basically get this nice local mesh structure which we can use to estimate the overlap volume. And also, if we have this locally refined structure, we can identify the subvolumes, which are in yellow in here, that are shared with that bound our overlap volume, and get these subvolumes to estimate the contact plane and contact normal. If we take a look at how to set up this in our dictionary, we have this virtual mesh entry, and it has two sub-entries, level and characteristic cell size. Characteristic cell size is standard or reference cell size in your simulation in absolute values. So if your characteristic dimension is 1 millimeter, this is 1 millimeter, and level is to how many refinement levels this characteristic cell size should be refined. So when the final subvolume, like this one, is smaller than characteristic cell size, refined to the level 3 in this case, the adaptive refinement in virtual mesh stops. That's one thing. One final note here, each contact pair or each contact has its own virtual mesh in our code. We don't construct one global, just a series of small local ones. And with this, let's go for the tutorials themselves. So first, we will take a look at spheres and fundamental settings. We will just take two spheres, let them go against each other, and check the effects of changing some basic DM settings on the sphere's behavior. Then we will take a look at non-spherical solids, so STL based solids, and we will examine the behavior of our virtual mesh algorithm. For this we will use our favorite glitters, so one glitter and several glitters will fall through your domain. And finally, as always, we will take a look at glitters and impellers. And with that, I will end this part of the presentation and leave you in capable hands of my colleague Ondřej Stujeník. We will go through the individual test cases. So
now, with the theory out of the hand, we can get to the hands-on session and try to set collisions of spheres and to prescribe fundamentals such as material properties, integration step, and let's see how it will turn out. All right, so now you should see my VS Code, and here is the structure of our repository, and we are today working in 03-DM, and let's start with the first case. First, have a look on which mesh we will be using, which will be rectangular with dimensions of 2 centimeters at x-axis, 6 centimeters at y-axis, and 2 centimeters at z-axis with following resolution. For the control dict, we will be running simulation towards this end time with prescribed overall integration step. Now let's go to the constant folder and let us open HFDIB-DEM dict. We are already defined two solids, sphere top, sphere bottom, which are predefined in the respective directories. Both bodies will be prescribed as fully coupled with velocities aiming towards each other. So sphere on top will be prescribed at position 1.5 centimeters on y-axis, and sphere bottom will be prescribed at mirrored across the origin at negative 1.5 centimeters on y-axis. Diameter of both spheres will be set to 1 centimeter, and the velocities will be set to 1 and negative 1 meters per second. Also, the material properties will be the same. So we will prescribe them with density of glass and with material called particle. Let's have a look on how the material particle is defined. So it's defined here with Young moduli at 5e7 pascals, and with all other values set to 0 and coefficient of restitution set to 1. We will see no dissipation. Also, the curvature is set to 0.55, which was mentioned earlier, and rotation model will be used this. We will use this following. And now let's get to the last part, but the most important, which is the integration step. We may now keep it on 1 and see what will happen. So let's load OpenFOAM and enter our directory. Yes, 03-DM and 1. Now we are here and we can run our simulation. So the simulation ran, and we can now open it in ParaView. All right. So we will use contour filter to load 0.5 to load isocontour at 0.5 value of the void fraction. So we can see that we have top and bottom spheres. And we can also include the outline of the domain, so we know when the particles are leaving the domain. Yes, turn it on. Okay, so let's go. Yes, and as you can see, the particles gained far higher velocity than they have before. We can also check this using the bodies info, where we will open the initial time for one particle, and we see that the velocity is negative meter per second. In the latest recorded time step, the magnitude of the velocity is 6 times higher, which is not good. This means that the integration is not set correctly. So let's change this to the 1/10 of the prescribed CFD step. Let us clear our case. Let's refresh it. Yeah, and now we can see that this is more like it. So you can also see that now the magnitude of the velocity at the beginning and at the end of the simulations are almost similar, and we have error at the 4th valid number. So that's good for some engineering applications maybe, but let's see if we can how much does the result improve. So let's clean our simulation again. Let's run it. Okay, so it's running. Let's go back to ParaView and let's reload. Yes, here, refresh. Okay, so we see that almost nothing has changed, which is good because the result, the prior result was almost good. So again, the original magnitude of the velocity was 1 meter per second, and at the end is almost similar. It's now slightly lower, but I believe that at 7 valid number, error means that the result is quite good. For the interest, we can try to call Python and let's assess what the collision time should be. We will import NumPy SNP and let's go. So characteristic dimension of the sphere was 1 centimeter. We multiply by pi, multiplied by square root of density, which was set to the following value, and Young moduli, which is set to this. Also, it's reduced value of Young moduli, so we can divide it by 2. And this is estimated time which collision takes. And this is the time required, and this is the time step prescribed by our solver. So at the start, with integration step of 1, we gave solver exactly one time step to assess to resolve the collision. Once we divide it by 10, this was already quite good result, and by 100, this was supposed to be our integration step. Since the CFD step is overall integration step is quite smaller, is already not quite, but a little bit smaller. I believe that we met the condition I showed you earlier. Okay, so let's quit Python. Let's clean our case, and with the correct integration step set, we may now try to meddle with dissipation. So I will change the value to 0.95, which by the definition of coefficient of restitution should mean that only 95% of initial momentum for the contact pair will be preserved after collision. So let's see. So the simulation is running. Not the significant change here. So let's have a look at the yes. Okay, so this is a little bit less than 95%, but that's not accurate. So yes, we can see that some dissipation occurred. We can see that also at the second body. Okay, so let's carry on. So now it's 0.8. Now we have 80%. Now I won't waste time with ParaView because we can barely see anything in there. And let's have a look here. So it wasn't, yeah, so finally. Okay, so now we are at 0.78 meters per second, which is almost 80%. Good. Okay, so let's try to push it to its limits, and let's prescribe the lowest value which is recommended to not trigger division by 0 according to the definition. So bash or clean. Okay, case is clean, and bash or run. Okay, so case is running. Okay, finished. So let's have a look in ParaView, because now we should really see some difference. Okay, great. So you can see that particles almost stopped, because the repulsion wasn't as before. And now let's see the end time properties of the body. Yes, so it dropped almost by 80%. So see, this is not this is just a small estimate, because in this implementation you won't get dissipation of 95% of momentum, but just 80. So yes, but to give you a general sense on how to prescribe dissipation, I believe this was sufficient. So let's go back to the presentation. All right. So this is what we did. The initial case, the overestimation due to integration, correction of integration, and then with dissipation. So now let's start to play with STLs, as our solver is mostly focused on non-spherical particles, and to enable virtual mesh again. We will start with one STL based body, which will collide with the prescribed boundary. And then we will try to add more bodies to the bottom of the domain and see how they will settle. So let's get to it. So again, you should see my VS Code. And we now want to enter the second category. I will also close it here. So the mesh, as you've seen in the original picture, remains the same as for the case of glitzers and impeller. And the control dict is prescribed that we will at following end time with the same integration step and right interval. So let's go to the HFDIB-DEM dict. So we already keep the prescribed integration step, which we concluded on before. The same material properties for the particle, and we can prescribe wall a little bit less stiff, or we can keep it the same. It shouldn't matter, but so no, I will keep it at 1. Now we need to describe the collision patch. So since our domain has following dimensions with the y minimum position of -3 centimeters based on a scale, I set the plane point to 0 on x-axis, -3 centimeters on y-axis, and 0 on z-axis. If I would change these numbers, it shouldn't make any change. But I like to place my plane point into the center of the boundary. Normal vector is prescribed to point outside of the domain, and I will prescribe the collision patch with the material wall. Now let's get to the virtual mesh. So if we run block mesh here, we can see that cell size is 1 millimeter. So I already set characteristic cell size at 1 millimeter, and let's try if 1 level of refinement will be enough. The glitter is again prescribed to density of glass with material particle, and yes, we don't want any refinement, and we will add the glitter once. All right, so okay, not to forget, because we are not prescribing any initial velocity to the glitter, we will also turn on the gravity to pull for the glitter. So we'll save the changes and run the simulation. Okay, so it's running. In the meantime, I will open a new render. I will delete these old, and I will prepare the view. Okay, it haven't finished yet, so we will wait a little longer. We are almost in a half, so let's wait. Or maybe you can bypass. Let's see. Yes, we may also try to bypass the wait by creating the sum.foam file. Okay. I will. Okay, sum.foam, which will allow me to load the case. I will disable the compose polyhedron. And yes, good. So I can now see the case, and I see that it's almost finished. So good. I probably rushed myself, but I don't care. So let's see an outline, and let's set a contour. Apply. Good. Here again, set outline. And I want to see all the cells registered by the body. So I will apply threshold, lambda 0.1. Okay, so above 10%. So also I will color it with lambda. So let's see how it will look. So the gravity starts to slowly pull the glitter towards the bottom boundary. So it's slow. Now let's see collision. Okay, it's not that terrible. Let's have a look. So virtual mesh 1. the glitter hit. So you can, okay, so glitter hit, so glitter hit the wall around this time. So let's see what is in bodies info. So 63. So this is velocity before the collision. This should be velocity right after. So okay, let's see if it changes with increasing level. So we can try 3. So now we know that this is our velocity. Store it somewhere. Create the file here, and I will store this. Okay, clean the case. Let's run it. So again, we can, yeah. So let's refresh it. How far are we? So let's wait a little longer. Okay. Yes, so now we see that with higher resolution, we almost doubled, or between doubling and tripling the velocity. So again, even though the result seems fine, we have no dissipation, and there is still gravity pulling against the particle, but still these results should remain the same. So this is how you can see the influence of the virtual mesh setting on your simulation. You can again try it with higher level if it changes. Just please know that I won't do it here because it already takes a while to evaluate. So we can now try to set. Okay, so I will skip the dissipation for the moment, and no, I will set the dissipation to 0.5, which I had already prepared here. Here I will set it to 0.6, and I will also turn on dissipation of rotation to 0.1, and I will also do it here. And I want to shift towards that I will not enter one glitter, but I will add multiple glitters at the bottom. Yes. Okay, and so without further ado, let's run the simulation. But since we already waited a while before the simulation with one glitter finished, I have these results already evaluated, so we can check it. So let's open it here. Right. So let's set outline and contour at, yes, almost. So yes, these are our glitters at the bottom, with the bottom patch still prescribed as a contact plane and gravity turned on. So again, and for the second view, I also want to see the cells So again, I will set outline and threshold for the cell data, and I want to see the cells which have, again, more than 50% of volume fraction for the body. So, okay, so I can see them here. This is maybe too much. Let's see how the particles will settle as the gravity pulls. So they are settling and they are bouncing here, as we can see here. But they are not turning. I would expect them to like turn and fall to the patch. This is due to the settings we forgot to change, or we didn't change so far. I can stop this, which is update torque. So even with tangential forces enabled by enabling me, the fully coupled body is forbidden to turn with this set to false. I will now set it to true, and I will run the case again. But again, I don't want to waste your time with waiting, so you can pause the video and run your simulation now, and then compare your results with mine. So we'll just reload the case. Yes. Okay, so we have, due to the random F model, we have different positions. So let's run it and let's see what will happen. So the particles are again being pulled towards the bottom by the gravity. But slowly but surely we can see that they are bending due to the contact and torque, which forces particles to rotate. These two are standing on the edge. Okay, that's cool. Yes, please remember that only the bottom patch is prescribed to be collision patch. So the other patches are not visible to the particles. So yes, let's fast forward to the end. Nice. So two particles are standing on the edge and the other fold on. Yes. If you are not happy with this and you would like to see a higher resolution, you may, because there is that bodies info folder, and it stores not only information regarding the movement of the body, but it also stores for non-spherical bodies their position of their templates, the STL meshes. So I can load them into the para view and we can have a look. So I will disable the contours. Yeah, and here you can see how the particles with original geometries settled on the bottom. So this is our result. So keep in mind that even though you have material properties and DEM properties all set, you still need to enable rotation for the particles so they can behave naturally. So this would be all to this tutorial regarding the STL collisions and virtual mesh. I can stop this and let's go back to the presentation. All right, so now let's implement our new skills to the glitters and impeller case. So we start with, last time we started with particles moving up towards rotating impeller, but passing through it because no collisions were prescribed. Now I hope that we make them to run around the impeller, interacting with it, and with the green highlighted patches. So let's go back to the VS Code. Okay, we are here. And let's see what changed in the case. So let's go to HFDIB-DEM. So we have still defined impeller and glitter. Here we have set this DM step, integration step. And because we are using glitters, which are more or less bodies with large flat surfaces. We will use the curvature coefficient to be set to 4, as we did in a previous tutorial, which I completely forgot to mention it. We will use following material properties for the particles and boundaries, and here I already prescribe all of the boundaries, and I also included the front and back, which we won't use, but if you would like to see, you may try. I will keep virtual mesh at level 3 with the characteristic cell size, and for the impeller I change nothing, so it will remain prescribed transferred body. I only increased its density to the glass, as we did before, and even you might now notice that update torque is disabled, but the impeller still rotates. This is because this settings is valid only when the rotation is being directly evaluated. Now it's prescribed, so it's basically it's here, but it doesn't matter. And again, material is set to particle. For the glitter, we only again change the density, and we keep its velocity at 10 centimeters per second in the direction toward the impeller, and we change this setting. Yes, now we change it, so the rotation will be updated, and we will keep this at model active, and material is prescribed to be the particle. Now to the control dict, I extended the end time to half a second of simulation time, because we want to see if it really works, and we can see it goes on longer simulation. So I will run it. I just need to change the folder. So bash will run. And again, while the simulation is running, I won't be waiting here till it stops, because I have already pre-evaluated it. So let me just, okay, I can move here to the, no, you know what? I will delete these, and I will change the path again to this, because I can keep this. So yes, and here, apply. Okay, so here, yes, I will modify the threshold. So I want to see everything. Okay. I will move to the initial time, and here I will enable contours. Yes, so you can see this, the both screens. So let's see how it will turn out. So our impeller is rotating. Oh, we have a different, I will just sync the views. Okay, and to have a, so our impeller is still rotating counterclockwise, and the particles are, yes, so now we can see that it collided. It's slowly but surely, it does what we told it to do. So now we have a running simulation where we have interactions between the impeller and particles and the boundaries. I believe that, yes, you can see that as the front boundary wasn't prescribed, the one body just left the simulation. So this runs. It's quite cool, at least I think so. Yeah, again, some particles are leaving the simulations as the collision of impeller push them out. Yes, here are particles bouncing at the boundary. So let's see what will be the end. Yes, so we are here. Okay, so you can run it yourself. You can run it even further than 0.0 seconds and see the results. You can also alter the settings of the virtual mesh or integration step and see how it differs, because some collisions might be still not solved properly. You may check our settings with the formulas we show you today. But from me, regarding this tutorial, it will be all. So I thank you for your attention. So far, we already covered the whole course. And in the next video, we will look on how to add the influence of the fluid into our simulation. So since this topic is quite extreme, in next video we will only cover the finalizing our goal. So with this, I thank you again for your attention. And if you have any feedback, please let us know. Have a great day. Bye.